Hey, can you see my screen?
No.
No. Oh, okay. Yeah, I thought wait. I thought
Okay.
wait. Okay.
Yeah, it's fine now.
Okay, right. Just now I don't know what happened. Okay, right. Okay, thank you. Right. So I was explaining about the MC just now before we took a break, which is a bit late actually. So close to buka puasa. So anyway, okay, so the aim here is if I were to repeat it, is we want to build or we want to construct, a Markov chain such that our posterior will be the stationary distribution of the Markov chain, right? So if we run the Markov chain long enough, right, and we start from any initial point, so long enough, okay, so that one is also we discuss later. Long enough, how long is long enough? So anyway, in theory, long enough, right? Then in the long run, the sample will be from our posterior, which is our target distribution. And it's also the stationary distribution of the Markov chain. Okay, so this means that if we get the sample from the posterior, then the average will converge to the station under the posterior distribution. Okay, so the most popular MCMC method is the Metropolis Hastings, and under a special circumstance, then the Metropolis Hastings will reduce to Metropolis. Okay, so for the Metropolis Hastings, so the idea is going to be similar to the important sampler, right? Because we are not going to sample from the posterior, but we're going to sample from a proposal distribution, right? So our posterior is the target, right? So this is our posterior. Then the transition kernel, right? So transition kernel is when we want to move from, so we want to move from theta A to theta B, right? So the transition kernel is actually theta A to theta B. Okay, so this is actually the transition kernel of moving, going to theta B given that we are at theta A. So this is how we write the transition kernel, right? And this is also called the proposal distribution. Okay, meaning that if we are at theta A, right, we want to propose to move to a new position, which is at theta B. So the Q is actually our distribution or the density function for the distribution of the proposal. Okay, so if we have the algorithm, then first we must start from somewhere. So we have a starting point. So for example, we have theta naught. So at time 0, right, we start at time. So this is actually at time 0, right? So we have time 0. We start at theta naught, right? So this, and then we want to move from theta, sorry, from theta, not theta naught, sorry, the T0, not theta naught. It's actually T naught, right? We have T naught, which is at time 0. Then we want to move to a new time. Okay, so in general, right? In general, so this iteration T means that we want to go from T minus 1. We want to move to T, right? In general, so we are at T minus 1 now. We want to move to T. So then our proposal, right, our kernel will actually be Q theta star, right? Because we propose to move to theta star at our current position, which is at theta T minus 1. Okay, so we actually, so from theta T minus 1, we want to propose to move to theta star. So this is called the candidate or proposal point. Okay, right. So with the Metropolis Hastings algorithm, there is actually acceptance probability. So acceptance probability means that we can either accept or reject the proposal. Okay, so before I go into that, right, so what do I mean by accept or reject? Okay, so when I say accept, right, so we are currently at T minus 1. So we are currently at theta T minus 1. right? So there are actually two options, right? Whether you are to accept or reject. So meaning that if I were to accept, right? If I accept, then I will move from theta t minus 1 to theta star, right? Theta star. Okay, so meaning that my new theta at time t would be theta star. Okay, so this is if I accept the proposal. So if I reject the proposal, right? So meaning that so there are two options. If I reject, right, then I will stay at the same place, meaning that my theta t is equal to my previous theta t minus 1. Okay, this is mean by acceptance probability, right? So meaning that with this acceptance probability, there's a probability alpha. So this is alpha, right? This is alpha. There's a probability alpha that I will accept the proposal. Okay. So you can see right there are two options. Either I accept or I reject. So if I accept, I will move to a different value of theta. But if I accept, I stay at the same place. Sorry, I stay at the same value, not same place. So I still move to t. The time will move, but the value is the same. Okay, value is the same. So if so meaning that I can change my value. If I accept, I change my value. If I reject, I do not change my value. So my value is the same. My previous value and my current value was going to be the same. I don't have do any changes. Okay, so how do we do this acceptance or so it's actually similar also to acceptance rejection, right? So in this acceptance, we're going to calculate this alpha, right? So you can see over here, this is minimum of 1 because this alpha is actually a probability. So it's between your alpha is between 0 and 1, right? Alpha between 0 and 1. So the minimum is because this one will not be because okay, this one are all density, right? If you have a probability, it will be 0 or larger. So this value, this ratio will not be negative. This value will always be positive, meaning that it will also be between 0 and 1. Actually, including 0 and 1, actually can include 0 and 1. Okay, so this one is negative. This is also between 0 and 1, this ratio. But this ratio can also be bigger than 1. Sorry, this ratio can be bigger than 1. So this can actually be, it's actually bigger or equal to 0, but can also be bigger than 1. That's why we have a minimum of 1 here, right? So meaning that if this ratio is bigger than 1, then it will become 1, right? But if it's less than 1, then you choose this ratio. Okay, right. So what is the ratio? So this P is your posterior, right? So you can see here, this is your P, this is your posterior. So this is a posterior under your proposal, and this is posterior under the previous value. Okay, so the top one is actually the probability of if you're at T star, you want to move to T minus 1. And the bottom one is actually if you're at T minus 1, you want to move to T star. Sorry, not T star, theta star, sorry. So the top one is actually if you're at theta star, you want to move to theta T minus 1. And the bottom one is actually if you're at theta T minus 1, you want to move to theta star. Okay, so so your P is the posterior, your Q is the proposal density. Okay. So then after you find this alpha, so alpha is between 0 and 1 inclusive, you generate a uniform 0, 1. Okay, so you will have a value. So meaning that you have a uniform. So U is between 0 and 1, right? So you choose, you generate a random value, U. So U is any value between 0 and 1. So you compare your U with alpha, right? So if your U is less than alpha, okay. So this is your U, right? So for example, if your U is less than alpha, then you accept. If U is less than alpha, okay, right. So meaning that U less than, so alpha is here. Okay, so this is your alpha, right? Okay, so meaning that you calculate your alpha, right? So if your U is less than your alpha, meaning that you are in this area, then you accept. So this is called the acceptance region, right? You accept your acceptance region. So if your U is in here, your U is bigger than alpha, you reject. Okay, so this is just to make it also like random, right? So we introduce a random U. Okay, meaning that if I have a value alpha, I can either accept or reject. But if my alpha is very large or close to 1, the probability of accepting is higher, right? Because the area of the region of acceptance is higher. Okay, so this means that if you have a higher alpha, then it is a higher probability of being accepted. Okay, but even though your alpha is high, there is also a small probability of being rejected. So you can still get rejected, but very small probability. For example, right, if your alpha is 0.8, right, very high, but suddenly you get your U is 0.9. So even though your alpha is high, you can also get rejected, right? But it's just a smaller probability. Okay, so anyway, so this means that then this means that we will accept the proposal with probability alpha, which is denoted by the function. Okay, meaning that probability alpha is we are at theta t minus 1, we want to move to theta star. Okay, so we can either accept or reject the proposal theta star. So we do this, you do this at all the iteration t, right? And then in the end we have a value. So meaning if we have with theta, start with theta 0, then we'll have theta 0, theta 1, theta 2, theta 3, then up to the number of iteration. For example, maybe theta n, right? So if you have n number of iterations, then you have n values of your theta. Okay, right. Okay, right. Okay, so and if your transition kernel is symmetric, right, meaning that the kernel of going from B to A, the kernel of or the property of going from B to A and the property of going from A to B is equal, then this is called the kernel is symmetric. Okay, so if they are symmetric, then actually this is going to be a simpler version, and this is called the multiplicity algorithm. Okay, so it's actually the same as the original one, but in the acceptance probability, then the kernel actually cancel out each other. Okay, all right. So what I mean is, right, so if you see in the original one, right, if the kernel is symmetric, then this part here, this part actually, right, because they are symmetric, then this actually cancel out. Okay, it's because they are symmetric. So that's why you only get the density of the posterior only, and the kernel actually cancel out. They actually cancel out. Okay, that so if you have a symmetric kernel, then that will happen. So you will have a simpler algorithm, right? And the alpha is simplified only by the posterior kernel or posterior density. Okay, in general, we will not know the normalizing constant, K or C, whatever, right? As I said before, right, if you have the posterior, right, if you have the posterior theta, even Y, so you have your C, and then you have your likelihood, right, and your prior. So usually C or K, whatever, say here we use K again. So if we have K, then we don't know this value of K, because all the time we are using proportional, right? So we don't know this normally constant K. All right, but here with the multiplicity testing algorithm, we don't even know even have to know K, right? Because since the posterior appear in both the top and bottom, for example, right, we have this, we have K here, yeah, we have K here, right? So because the K appear in the top bottom of the alpha, So they will always cancel. So this actually cancel out. The K cancel. So even though we don't know the full posterior, we only know the conditional posterior, right, with some function. So it doesn't matter because the constant will cancel out, right? So we still can use this algorithm even though we only know the posterior up to proportionality. So this is what I said before. This is the advantage of the MH multiplexing algorithm. Even though you know only the proportional part, right? It's okay. You can still use this algorithm. Okay, right. So if we look at this alpha, right? So what does it mean? So if the proposal increases, the posterior density, the proposal increases the posterior density, we will always move to the new point. Or the proposal decreases the posterior density, we will move the property equal to the ratio. Okay. So what does this mean? Because if you look at the alpha, because I think we have to look at the previous alpha, right? So if you look at this alpha, right? So if the proposal increases the posterior density, meaning this part, right? So if this part is big, right, and this part is large, then this minimum, this function, this function will be bigger than 1 maybe, right? So your minimum is 1. So if your alpha is 1, then you will definitely move to the new point. Okay, but if your proposal decreases, meaning that this ratio, if this ratio is less than 1, then your alpha will be less than 1. Okay, but so if less than 1, there is still some probability to accept. As I said before, right? If you look at this graph, there is still possibility of accept. So even though your alpha is small, there is also a small chance of being accepted. So meaning that you can still move to the proposal value, right? Depending on the value of your alpha. So this is still a chance. So even though it's a small chance, there's still a chance. But if the theta star will increase your posterior, then you will surely move like your alpha equals to 1. Okay. So this is what they meant by, if so, meaning that with this alpha, then you also have a chance to either move. I mean, you can move surely, or you can move with the property alpha. Okay, right. Then, okay, so now we're going to look at example, right? How do we actually do this multiple testing? Say that we have a kernel. So we have the posterior is a normal 0, 1. So this is actually very simple, not really like what our Bayesian, right? But this is just for illustration. We have our target is the normal 0, 1. And then we want to use the symmetric proposal, which is a normal theta sigma square, right, as the proposal, right? So we have to describe the algorithm for this case. Okay, so then your target, right? Maybe you can just write your target is your normal 0, 1, right? And your proposal is a normal. Okay, so this means that the proposal depends on the current value of theta, where the theta is your mean, right? And you have the mean and your variance sigma square, right? So when you say symmetric, right? So symmetric means that the probability of moving from theta to theta star is equal to theta star to theta, right? So actually we are reduced to the Metropolis algorithm. Okay, so actually how do you see this asymmetric, right? So if we write the kernel, right? So if we write the kernel of the normal, right? So this is normal, right? The normal, we have the variance, and then exponential. Right. So if you look at this, right, if you have the mean is theta, right? So this is theta star minus theta. So this is the mean where is theta, right? But so this is actually this is actually normal theta sigma square. Correct. So meaning that the parameter here is theta star. Right, the parameter is theta star. So meaning that theta star has a normal distribution with mean theta and variance sigma square. So the reverse, if you have the reverse, which is theta given theta star, meaning that here this means that you have normal with mean is theta star, variance sigma square, right? So this means that your parameter is actually theta. Okay, so you can see this why you have to be aware of the notation, right? So this means that the mean here is theta. Okay, so if you have theta given theta star, this means that the mean is theta star. Okay, but if you look at the PDF for normal with mean theta star, where theta is your parameter, right? So if you write the PDF, it's actually exactly the same because it's a square function, right? You have theta minus theta star square, right? Okay, so here, but in the first function, the theta is the mean. The second function, the theta star is the mean, right? But because this is a square function, then this is equal to this, right? So because this is equal to this, then that's why the the proposal are equal, are symmetric actually. Okay. So because of this, then it's reduced to we have the Metropolis algorithm. So we have the Metropolis algorithm, right? So first we have our proposal, right? So we have to choose we choose our starting point. So we have theta 0, right? Of course, when you choose the theta 0, make sure that it's inside the posterior, right? It must be such that the posterior is positive, right? Then, you just write the algorithm at each iteration. Then we propose our proposal, right? So our theta star is normal, right? But this is where you have to make sure, right? Because the t depends on t minus 1. So your proposal theta star depends on theta t minus 1. Oh, wait. I think if I forgot, because I always change the notation t minus 1. Okay, so the theta star depends on t minus 1. Okay, right? So we propose our theta star, which is normal and the mean is the previous theta t minus 1. Then you calculate your alpha. So your alpha actually is a function of your t minus 1 and the theta star. Okay, and this is the mean of the function. And because this is only Metropolis algorithm, then you only have the posterior, right? And you can see, right, if you have the Metropolis only the Metropolis algorithm, it only depends on the posterior. So this means that if your theta star increase the posterior, then you will always accept the proposal theta star. Okay, so you don't depend. Oh, okay, I don't have, right? So then you actually have to write the whole function. Okay, so if you use the normal kernel, right? So meaning that you have to use this normal kernel, right? And after you simplify it, because I'm running, I don't have space. Okay, then after you simplify it, then you will get this function. Okay, this one is after you simplify, and you have to divide the exponential. So when you divide the exponential function, you become minus. So, oh, okay, wait, I'm using t. Okay, so I think the problem is I change my notation. Okay, but then the problem is when you do t1, okay, square, right? Comma, oh, too much bracket. Okay, right, and then yeah, because I don't have. Then you have, okay, so when you do this, you have to write everything. So if u less than alpha, you accept. Sorry, I running out of space. The star. If not, theta. Wait, it's not theta t. Okay, right. Theta t is theta t minus 1. Okay, right. So if when you're doing this means that first, if you are symmetric, then you have to you can use the metropolis algorithm. Then you have the proposal. So you have to put the density, well, or up to proportionality, right? So you can see, right, if you, even though you have this standard normal. Oh, wait. Oh, okay. Right. Okay. Oh, no wonder. Okay. Yeah, all right. Sorry, I thought I have enough space, but as usual. Okay, sorry, it's not that normal, because sorry, so your P is actually your standard normal. Okay, so okay, maybe I'll just add here. All right. What is because P is standard normal, right? So your P, I'll just add here. Your P is actually 1 over 2 pi. So it is not a Q, sorry, that's not your Q. It's actually the standard normal. So it's actually this theta square. Yeah. Okay. Right. So actually you cannot use your Q. Sorry, you are using the standard normal density because your proposal, sorry, your posterior or your target is actually a standard normal. So this is the density for the standard normal, right? So you have theta star here. So you can see, right, your 1 over square root 2 pi will cancel. So you're only left with exponential minus 1 over 2 theta square, right? So the top one will be theta star square. The bottom one will be theta t minus 1. So that's why you get here theta star square minus theta t square, t minus 1 square. Right, so that's why you get this function from the standard normal posterior. Okay, yeah, so yeah, I missed it. Sorry, it's not using the Q, it's actually using the standard normal density. Okay, so you can actually, so meaning that now, if you were to calculate the alpha, then you actually calculate this function, then you actually compare it, and then you get alpha, and then you generate a uniform 0, 1, and then you compare uniform with alpha, whether to accept or reject your proposal. Okay. So if you reject, this means that even if you reject, then you still get some, you have some value, but it's the same as the previous value, which is theta t minus 1. Okay, right. I think okay. I think this is a good place to stop. I think we will actually continue next week.
Can I ask a
Okay.
question, please?
Okay, sure.
Yeah. How do you find the proposed
Proposal.
distribution?
Okay, right. So in this example, because it's just example, right? Okay, so in this is just example, so that's why we choose this. Okay, so it's going to be your proposal is depend on the, sometimes it depend on the shape of your target, right? Your posterior, but it's also depend on the range of values. For example, right? If your target, your x is from minus infinity to infinity, right? So you have to make sure your proposal can also produce values similar to that, right? For example, right, if your x originally is minus infinity to infinity, don't use like uniform 0, 1, right? Because uniform 0, 1 is only 0, 1, right? So you cannot go beyond that. So it's also, first you have to look at the spread or the sample space of your x. Okay, so at least it should match, right? Or at least you can travel along the space of your x. Okay, but also sometimes it depends on the sampling. It also depends on how efficient it is. Okay, and also after we use it, you can actually check whether later we learn about the mixing, right? Mixing means, right, does it actually produce a sample from the whole range of x? I mean the target. Okay, so there's no wrong. Okay, there's no wrong proposal actually, as long as you can get all the values of x out. I mean the target, you should be okay. But it's going to be whether it's good or less good. Okay, so the choice of the proposal is actually quite subjective. It's up to you actually.
So long as I match the support, then it
Yeah,
will
as
always
long as you
converge.
match support, right? Yeah, but okay, because it's not covered in our course, but it's also something called a random walk. So random walk means that you just add something. For example, if I'm x, I put x plus 1 or x plus sigma or x minus sigma. So I just add it to to increase or to decrease. This is also a random walk Markov chain. Sorry, random walk MCMC. So they're actually how to choose a proposal. There's a lot of ways actually. So it's not really covered in our course because it's too broad. But
So
this
this
is
is just so you're saying that this is just one form of a Markov chain, so that we can use other forms of
this is
Markov chains.
only, yes, it's only one point. So no, it also depends on your target. Okay, and because this is also univariate, right? So when you go up to multivariate, there's a different ball game, right? Because you have to generate each parameter, and remember, right? Each parameter. So now instead of it correlation with the time, it's also correlated with each other. For example, if I have theta 1, theta 2, right? Theta 1 will also depend on, so theta 2 will also depend on theta 1. So correlation with the time and also correlation with the each parameter.
I
So
see.
it gets like it gets messier lah as you do the MCMC for a higher dimension. So
Okay.
yeah, so sometimes also your proposal is also like try and error. You try, oh, it's okay. Then if you try it's not good, then you change.
I see.
So it's more like it's also like